Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, good morning. Now in Lecture 2, we're going to continue our discussion of the Landauer approach. Mostly what I'm going to be discussing in this lecture is this concept of modes and what it means physically. But we're also going to discuss some applications of this formalism and connections to experiments to convince ourselves that this really does work in practice and describes experimental situations. So just by way of a quick summary, we have this simple model for a nano device. The device itself is described by some distribution of channels for current flow in energy. That's M of E. And by some transmission, some probability between 0 and 1 that an electron that comes in from contact 1 goes out contact 2. Two large thermodynamic equilibrium contacts, but possibly with two different Fermi levels if we have different voltages applied to those contacts. We developed a simple expression for the current. Current is driven by differences between the Fermi functions of the two contacts, and we also simplified that expression for small voltages, linear response. And in that case, we got an expression for the conductance that was given by this last expression. Okay. Now, we talked a little bit about transmission and modes, and we'll get more comfortable with that as the course goes, as the course progresses. But I'll just remind you that I postulated this simple expression for transmission. You can see that this is a number between 0 and 1. It's 1 in the ballistic limit. It's very small, the ratio of the mean free path to the length of the device in the diffusive limit. But often these days, devices operate somewhere between those two limits in what we would call a quasi-ballistic limit, quasi-ballistic regime. And M is the number of channels, and it's given by an expression which, when you look at it, it's hard to interpret physically. But if I'm computing the number of channels from some given band structure, this is the way I compute it. It's Planck's constant divided by 4 times the average velocity in the direction of transport times the density of states per unit energy, per unit area, times the width of the conductor. So one of our goals in this lecture is to get comfortable with that formula and to understand what it really means physically. But first, let's take a look at just using it. We'll assume that this equation is right. Let's look under low current. This might be a low voltage between the drain and the source of a MOSFET. And let's calculate the conductance. So here's our Fermi function. It's 1 way below the Fermi level. It's 0 way above the Fermi level. It makes a transition right around the Fermi level. What's important is the derivative of that function. And notice that the derivative is peaked and has a sharply negative value around the Fermi energy. So minus the F naught dE, the term that's important here, is peaked near the Fermi energy, and it's something that I'll call the Fermi window. So it basically picks out which of the energy channels are important to current flow. The energy channels are those that are inside this Fermi window, and that Fermi window has a width of a few kT. So it's relatively broad at room temperature, very narrow at lower temperatures. Now, if I look at lower temperatures, then I can make a very simple approximation. This looks like a delta function. In fact, it has an area of 1, so it has all the properties of a delta function. That makes this integral easy to do. It's just a delta function peaked at the Fermi energy. So it tells us that the conductance is 2q squared over h times the transmission at the Fermi energy times the number of channels available for conduction at the Fermi energy. So we get a very nice, simple expression for the conductance. Valid at lower temperatures when the width of this derivative is very narrow and it acts like a delta function. Now let's look at experiments. This really does happen in practice. The physics was sorted out in the 1980s and early 1990s, and here's one example of an experiment. This is a two-dimensional resistor. Here are my large Landauer contacts. Then it's necked down to a region where the width gets very thin. Turns out that this width can be controlled electrically, because if I look vertically at this structure, there's a layer of gallium arsenide where the electrons flow. There's a layer of aluminum gallium arsenide which was actually doped, and the electrons spilled from the aluminum gallium arsenide into the undoped gallium arsenide. That's a technique that people call modulation doping, and it's a trick to get very high mobilities with very long mean-free paths. But around this, and not shown on the two sides, are two Schottky barriers, reverse bias junctions that can deplete the semiconductor, and that's how these experimentalists electrically controlled the width of the conductor. So if we measure the conductance as a function of the width of this constriction, you would expect that the wider it is, the higher the conductance, the narrower, the smaller the conductance. That's the way resistors work. But when you do the experiment, you find something very, very interesting. The conductance does increase as the conductor gets wider and wider, but it doesn't increase smoothly. It increases in discrete steps, and this conductance is plotted in units of 2q squared over h. So it starts at some level. If you make it a little bit wider, it increases by 2q squared over h, another 2q squared over h. So the important point is that the conductance is quantized in these steps of 2q squared over h. To understand this experiment, we would take our expression, because the experiment was done at low temperature, so we'll take our low temperature expression. The mobilities and mean free paths are very long, so we'll assume the transmission is 1. So what must be happening is that we must be changing the number of conducting channels discretely. So to understand this experiment, we need to understand M of E in a little more detail. So let's take a look at that. That's our main goal for this lecture, is to get a physical feel for what M is. So here's a 2D, say, ballistic channel. You know, electrons are free to move in the XY plane. There's some magnitude of velocity v moving at some angle theta to the XY plane. Now, if I ask what is the average velocity in the x direction, in the direction of transport, it's got to be less than the magnitude of v, because a lot of them are pointing at an angle. And if you just do that angle average, it's easy to show that the average velocity is 2 over pi times the magnitude of the velocity. So that's my average velocity in the direction of transport. Okay, let's use that and see if we can evaluate this quantity m and figure out what it is. So we have the average velocity in the direction of transport. If this is a material with a simple band structure, then 1/2 mv squared is equal to the kinetic energy, E, with respect to the bottom of the conduction band. So I know what the magnitude of the velocity is at that energy. If it's a two-dimensional sheet with a simple parabolic band structure, I know what the density of states per unit area, per unit energy is. So I can simply take these quantities, plug them into my formula for M, and this is what I'll get. Okay, it's beginning to look simpler, but we're still not completely clear as to what it is. Well, let's also remember that in a simple band structure, then the kinetic energy, E minus the bottom of the conduction band, is h bar squared k squared over 2m. Remember, we think of h bar k as crystal momentum, so this is like momentum squared over 2m. We get this simple expression for parabolic bands. So there's a relation between E and k. And remember that k is the wave vector. So the electron wave is propagating as e to the plus minus ikx. K is the wave vector, 2 pi over the wavelength. I'll call it lambda b, the wavelength, the de Broglie wavelength of the electron. So if I solve this expression for k, then I have basically, I see that what I'm solving for is the electron wavelength. So let me take this expression, plug it back into my expression for m, and re-express m in terms of the electron wavelength. Now we get a really simple looking expression. The number of channels is the width of the channel divided by the half wavelength of electrons at that particular energy. Okay, that's beginning to look like something we should be able to interpret physically. So this is what the formula says. It's the number of half wavelengths that fit into the width of the conductor. So let's see how that works, and this is also why people refer to the channels as modes because they're like modes in a waveguide. So if I think of my conductor like a 2D waveguide, there's an electron wave propagating along this 2D waveguide. And the electron wave is confined to be inside the conductor, so the wave function has to go to 0 at the two edges of the conductor. So if we take our expression, and I see that there is one channel when the half wavelength is equal to the width of the conductor. What does that look like? That means that what I have here is an electron wave where half of the wavelength fits into the width, so the wave function goes to 0 at both ends of the conductor and satisfies the boundary condition. Okay. So this is something that will happen at a certain value of ky. Okay. And it will give me an expression that looks like this. Okay. Now, let's take another look. Let's look at our expression. We can see that we have two channels. When the wavelength is equal to, when the wavelength itself is equal to W, then when I plug it into this expression, I get M is equal to 2. When the wavelength is equal to W, I fit an entire wavelength in. That also satisfies the boundary conditions. All right? That occurs at some value of ky, but a smaller ky means that there's a smaller wavelength that could also fit in. So in this case, I have two channels at this particular energy. Depending on the value, the direction that it's propagating in the xy plane, depending on the value of ky, I'll have a wavelength in the y direction that I'll have two possible conditions that will satisfy the boundary conditions, and those give me two possible modes. Okay, we can see that a little clearer if we look down on the top in the xy plane, and if I draw a circle of constant energy for this parabolic energy bands. If I have an electron that's propagating at some angle to the x direction, there will be some wave vector ky in the transverse direction. Okay, so that will give me a wavelength in that direction that's 2 pi over lambda 1, because I'm talking about the first ky. And, to satisfy the boundary condition, if a half wavelength is equal to W, I will have satisfied that boundary condition. Okay. Okay, but staying on this constant energy surface, an electron with the same energy, but with a higher ky implies a smaller wavelength. It has the same energy, but it has a smaller wavelength. In fact, if it has a wavelength of W, then the entire wavelength will fit into the width. I still satisfy the boundary condition. So for this particular case, I have two different values of k in the transverse direction, both of which give me wavelengths that satisfy the boundary condition. So at the particular energy given by this circle, I have two possible electron channels that will satisfy the boundary conditions, and those are the two channels. Okay. So that gives us a simple physical understanding of what's going on here. As you increase the width, we just increase the number of half wavelengths that can fit into the channel. Each time we do that, we get one more conduction mode. Each time we get one more conduction mode, we get one more channel. And we can only have a finite number of those because they're a discrete number of ky's that give me wavelengths that fit the boundary conditions. So that's what leads to quantized conductance. So you're all familiar with density of states. We use the density of states to compute the number of electrons in the device. But now we've introduced another quantity, the distribution of channels in energy. And we have an expression for that. So we use M to compute the current. We use density of states to compute the electron density. And most of you are familiar with what the density of states versus energy looks like in a two-dimensional semiconductor. It's just constant effective mass over pi h bar squared. But the distribution of channels for the same case goes as the square root of energy. So depending on whether I'm working in 1D, 2D, or 3D, I'll get a distribution of a density of states and a distribution of channels that will have different shapes. Okay. Okay, and I point out here that very important assumption, we're making an assumption that the energy bands are parabolic. If I have a different band structure, I'll get different results. So to recap, we've been talking about the number of channels. We have a formula that given any band structure, any dimension, 1D, 2D, 3D conduction, we can compute this quantity. So it depends on both band structure and dimensionality, but it basically has a simple physical interpretation. It's the number of half wavelengths that fit into this 2D resistor, or more generally into a 3D resistor. And we have transmission. And we have given you an expression that looks plausible, although we haven't talked about it in a lot of detail. When we talk more about scattering, we will discuss more about transmission. It depends on band structure, because that's what gives us this velocity. But it also depends on the physics of scattering. So that's something that I'll ask you to accept for the time being, and we'll get more comfortable with it later on in the course. Okay, now, just to conclude here, let's apply this to a 2D resistor that might be something like the channel of a MOSFET, so we can get warmed up for where we're going with MOSFETs. So looking down on the top, I have a contact with 0 voltage, ground, one where I apply a voltage. I have a 2D conductor. I have an expression for the conductance, or 1 over the resistance, that's given by our Landauer expression in the small voltage regime. Okay. So at 0K, the ballistic conductance, when the transmission is 1, is just these fundamental constants times the number of channels at the Fermi energy, EF. If I want the ballistic resistance, I take 1 over the conductance. It's just 1 over the number of channels times those fundamental constants. Those fundamental constants turn out to have a value of 12.8 kiloohms. So fundamentally, the resistance of anything is 12.8 kiloohms divided by the number of channels at the Fermi energy. Okay, so we use this to explain quantized conductance, but in a bigger conductor, the number of channels might be so large that it's hard to count, but still the same principles apply. Important to note that the resistance is independent of channel length, because the transmission is 1. Doesn't matter how long the resistor is, an electron that comes in contact 1 goes out contact 2. Okay. All right, now let's look at t greater than 0. Still ballistic, so the transmission is still 1. Now we have to work out this integral. Well, that involves a little more math, and I won't go through that today, but you can show that if you do that integral, I could write the result as 2q squared over h times the number of channels inside that Fermi window. And when you do that math, the expression for the number of channels inside that Fermi integral, inside that Fermi window, involves a Fermi-Dirac integral of order -1/2. So it's something that we can compute. If I want the resistance, then I just take 1 over the ballistic conductance, and I get the same sort of thing. 12.8 kiloohms divided now not by the number of channels at the Fermi energy, but by the number of channels in the Fermi window. Same kind of concept. Okay. Still, the resistance is independent of length because we're talking about ballistic conditions. Now, if we remove the assumption that we're ballistic, but begin with the t equals 0 case, then I can replace this derivative again with a Fermi function. What will be important is the transmission at the Fermi energy, and I'll get an expression for the conductance that will just be the transmission at the Fermi energy times the ballistic conductance that we got before. Or if I flip it upside down and look at the ballistic, or if I look at the resistance in the non-ballistic case, it's 1 plus length of the conductor divided by mean free path times the ballistic resistance. So if I plot resistance as a function of the length of the transistor, length of the channel, I'll get something that I'll find out that the resistance doesn't go to 0 as the channel length goes to 0. The resistance goes to this fundamental lower limit, this ballistic channel resistance, which is related to fundamental parameters and numbers of channels. Okay. Okay, we could do the same exercise at t greater than 0. It would involve Fermi-Dirac integrals. I'll just leave that as an exercise. There's no new physics involved in that. So to wrap up, these 2 lectures have tried to get us comfortable with this Landauer approach. Current is related to transmission, number of channels, and is driven by differences in Fermi functions of the 2 contacts. Under low bias, current is proportional to voltage, and we have an expression for the conductance. And we have simple expressions for the transmission as a function of energy, and for the number of channels as a function of energy. When the number of channels gets very small, we can just count the number of channels. When it's larger, we compute them with this expression. Okay, so we now have the mathematical formalism to understand diffusive, ballistic, and quasi-ballistic transport. We're now ready to apply this to MOSFETs, and that's what we'll do in the next lecture. Thank you.